Well, welcome back to the third installment of What is a Derivative in our Introduction to Derivatives. In this lesson, since we've already looked at calculating the path of a ball in space, we'll find out that there are other derivatives that are helpful to us in the science and engineering world. Now, this is hardly an exhaustive study, but just an introduction to some of the more basic ones. So let's take a look at a few. Let's go back quickly and review what we saw regarding how to take a derivative. We started with our equation minus 5x squared plus 15x plus 0. From the x squared term, we took the 2, we kept the minus 5, the 15x, x to the first power became x to the 0 or 1, so the 15 comes down as 15, and there's our solution. The first derivative of our equation is minus 10x plus 15. We've looked at a basic value to an exponent, x to the second power, y to the third power, algebraic expansion. Now we can look at some other common derivatives. One that's potentially troubling is the square root of x. The square root of x isn't really as hard as it looks. If we recognize that the square root of x is x to the 1/2 power, then we apply the rule we've already seen, and we're going to take that 1/2 out in front of the equation, and we're going to subtract 1 from the 1/2 to get minus 1/2. So the derivative of the square root of x is 1/2 x to the minus 1/2 power. The derivative of the sine is the cosine. We can see this if we look at a sine function and then we overlay a cosine function on it. But let's look at the sine function a minute. We know that it's moving upward at time equal to 0. And that its vertical velocity reaches 0 when it reaches 90 degrees. But at 90 degrees, if the velocity is 0, then the derivative, which is the velocity, the derivative of position is our velocity. That means the value of the derivative is 0 at that point. If we numerically follow it around, we're going to find out that at each point, we're going to be taking the derivative or taking a minus 90 degree phase shift from the cosine in order to create the cosine. And this would be a fun one to actually sit down and plot out point by point using a math function on a computer like Excel or some other to look at the actual results. Now on the same graph, we can look at the derivative of the cosine and make the same analysis. When the cosine reaches its maximum, that's at 90 degrees, its vertical velocity is 0. So that's where it's going to start, and it's going to follow the same path. But what we see is that that's exactly out of phase if we back us up the other way from the sine function. That's the negative of the sine function. So the derivative of the sine is the cosine. The derivative of the cosine is the negative sine function. Well, sometimes these things are happening at a faster rate than just simply the sine of the time value. So at higher frequencies, we'll have sine of omega t, and the derivative of that will be the omega, the radian rate, times the cosine of omega t. Again, the sine and cosine follow in order. Similarly, the derivative of the cosine of omega t is going to be the negative of omega times the sine of omega t. There are some other common derivatives that we'll look at. The first one is the derivative of the square root of x. Now, initially that looks like it could be rather complex. Okay, what are we going to do with the square root? But let's recognize that the square root of x is just x to the 1/2 power. Because it's x to the 1/2 power, we'll follow the same rule that we've used to this point. We'll take that 1/2 and bring it out in front. We'll subtract 1 from the 1/2, and we'll have minus 1/2 to give us the value of the derivative of the square root of x. We won't prove this one, but there are some functions where you'll be taking the natural log of a number. The derivative of the natural log, by definition, is 1 over that number. Another one that's used in electronics is e to the x power. The exponent, e to the x. The derivative of that, by definition, is e to the x. This is the one function that has itself as its own derivative. Our next step from here is going to be looking at some examples from electronics. Both of those we will use the e to the x. So come on back and we'll look at some electronics.